Okay, so we talked about the fact that heat is a transfer of energy. Well, how does it transfer it? And there's three main ways. Conduction, right? So heat basically, one molecule is really hot, starts to heat up, its temperature rises, it's going really fast, and then bang! It bumps into the next molecule, and it heats that one up, and that one starts going really fast, and then bang! It hits the next molecule. And so basically it goes from one to another and heats up the whole thing. There's a PBS video that's kind of cute about this.
Conduction. If you stir a boiling liquid with a plastic ladle, after a few moments, the ladle will become quite warm. The same will happen with a wooden ladle. And a ladle made of metal can even become too hot to handle. This is because the heat from the boiling liquid is able to travel up the length of the three ladles, quite slowly through plastic and wood, and very fast through metal. But how does heat manage to do this? How does heat travel through things? Well, when the hot liquid heats up the end of each ladle, its molecules, or in the case of metal, its individual atoms, start to vibrate more rapidly. And when the heated molecules, or heated atoms, vibrate faster, they start bumping faster and faster into their slower neighbors, causing them to speed up in turn, and bump into their neighbors, and so on all along the ladle. In this way, the increased speed of vibration, and therefore the heat, is passed on from molecule to molecule, or from atom to atom. It's like a row of dominoes knocking each other over. And this domino effect, which leads or conducts heat through any substance, is called, naturally enough, conduction. Non-metals, such as wood and plastic, conduct heat quite slowly. They are bad conductors of heat. In contrast, all metals conduct heat very rapidly. They are good conductors of heat. That's why the witch with a metal ladle got burned.
Another way to do it is convection, which is near and dear to my heart, but that's a whole other story. So basically, this is what you know, right? Cold sinks, heat rises, right? That's convection. Very important for the atmosphere, also for oceans, and there's a tie-in with the atmosphere and oceans, but that's not too much later. Another fun word is advection. It is basically convection, heat rises, cold sinks. However, instead of up and down, it's left and right. Here's another PBS video on convection.
Convection. But why does hot water go up and cold water go down? Because of the principle of buoyancy. If you hold something that is less dense than water, such as a cork, in the middle of a beaker of water, the buoyant force pushing that cork up will be greater than the force of gravity pulling it down. And as soon as you take your hand away, the cork will rise to the surface. Now, when water is heated, its molecules speed up and it expands and becomes less dense. And this less dense water will therefore go up, and then cool and become dense again, and therefore go down. Because the principle of buoyancy applies as much to gases as it does to liquids. When air is heated, its molecules speed up, and it expands, and becomes less dense. And so hot air rises, just as hot water rises. That's how hot air balloons work. When the air inside the balloon is heated up, it expands. And therefore, there's not enough room for all of it inside the balloon, so some of this hot air escapes. The result of this is to leave fewer air molecules in the balloon than before. In other words, the air inside is now less dense than the air outside. So the balloon floats upwards, just like the cork in the beaker of water. The fact that hot air rises also comes in useful when cooking a hot dog. It'll take forever to get hot if you hold it beneath a fire. But if you hold it just above the hot air which is rising up from the fire, you're in business. And since both gases and liquids flow, scientists refer to both as fluids. and to the type of heat transfer which carries or conveys hot fluids upwards and cold fluids downwards as convection.
All right, so the last one is radiation. And radiation is also important because it's how we heat it up, right? The sun, the radiation travels through space and hits us, and it provides us with both light and energy. So what we see is something called visible light or white light, and there's a whole bunch of other types of radiation, and we'll get into those in a minute. But first, let's watch the PBS one on radiation.
Radiation waves. If you touch something that is very hot, you'll get burnt. This is because of conduction. The heat is conducted by a sort of domino effect from molecule to molecule, or from atom to atom, along the hot object and into your fingers. That's one kind of heat transfer. But if you hold your other hand above the same hot object, you will also get burnt. This is because of convection. The hot object causes the molecules of air above it to speed up. The hot air expands and becomes less dense, and is therefore conveyed upwards. That's a second kind of heat transfer. Are these the only two ways that heat can be transferred? Then why are you sitting under that beach umbrella? Because the sun's too hot? But how can the sun transfer heat to you? You're not touching it, so there can't be any conduction, can there? And since most of the space between you and the sun is just that, space, except for the thin layer of air formed by the Earth's atmosphere, there can't be any convection either, can there? Because once you get beyond our atmosphere, there's almost nothing out there to do the convecting. But the sun still feels hot. Amazing. How is that possible? Is there a third kind of heat transfer which allows heat to move through empty space? Yes, there is. And to understand it, you must first of all remember that heat is a form of energy. Now, energy can travel in various ways, but one of the chief ways in which heat energy travels is in the form of waves. Rather like the waves that a boat makes when it moves through the sea, or the waves that spread out when you drop a pebble into a pool of water, or the waves that travel along a rope if you jiggle one end of it up and down. In all these cases, what you are seeing is the effect of the movement of energy itself. By means of waves, energy can move through any distance. You can do it yourself. You can make that umbrella move without touching it. Tie one end of your rope to the umbrella, and now move your end of the rope up and down. You can actually see that your energy is traveling through the space between you and the umbrella, and then making the umbrella move. The heat energy from the sun travels like that. The sun sends out waves of heat energy in all directions. Each of them is rather like the spoke of a wheel, and this is exactly what scientists call them, only they use the Latin word for spoke, which is radius, from which they get the word radiation, the name given to this third kind of heat transfer. So it's by means of radiation waves that the sun can transfer its heat energy to you and make your molecules go faster and therefore make you hotter, even though the sun is millions of miles away. Just as by means of waves again, you can transfer your energy to the umbrella and make it move, even though you're standing several meters away from it. But it isn't just the sun that radiates heat in all directions. So does an ordinary fire, or a stove, or an electric light bulb. In fact, waves of heat energy are radiated to some extent by all sources of heat. Even you radiate a certain amount of heat in the form of waves. Come to think of it, there are waves everywhere. Oh, watch out. Here comes a big one now.
Alright, so I like that they point out that even you radiate, right? So now we know from previous video that you matter and you are radiant. I mean, come on. Those are good things to be told. You matter and you're radiant. Okay, so here is the spectrum of radiation, right? And higher energy over here, lower energy over here, and this is visible or white light. So this is what we get to see. This is what we get to see. This tiny little bit, right? If we start at the high energy, you got gamma rays. And then you have X-rays, right? Those are the ones that they look at your bones, right? You break a bone, you get an X-ray of it, right? And then you have ultraviolet light, and this is also known as UV, which is the one that turns you a nice tan, right? And again, mine is the lovely shade of lobster. And then you have infrared. Now, this is also known as night vision, which I think is pretty cool. I love watching the shows and seeing the night vision. And then you have microwave. And finally, you have radio waves, right? So, cook your food and listen to the radio. Those are the types of waves. So again, visible. This is all you get. So I love the people like, oh, well, I'll believe it when I see it. Really? Really? Because you know how much you are not seeing, right? A lot. All right, so radiation can't just be as simple as radiation. You have to have laws of radiation. So here's one of them. All objects continually radiate, right? Which goes back to the whole you are radiant. Here's another one. Hotter objects radiate more than cooler ones. Duh, right? This guy here, he's holding a cooler object. This is a hot object. Notice he's not grabbing the glowing part. Why? Because it's radiating more. Right? Now, objects that are good absorbers of radiation are also good emitters of radiation. Usually black and white, right? Black absorbs and radiates. White, not so much. Right? This is usually the time in the classroom, like, okay, everybody get together and we're all going to go outside, right? And we're usually at HCC where they have blacktop pavement and next to grass. And so I'd go out on the blacktop, and if you don't have a blacktop, I mean, we're not together, so go on outside, right? And if your car is sitting outside, whatever color it is, if your car is sitting outside, just put your hand on top of it. Hopefully it's not a white car. Put your hand on top of it, and you'll feel the heat coming up, right? If you have a blacktop, like the road, right? No, I'm not going to tell you about the road. Just put your hand over top of the car, the hood. You can feel the radiation coming off of it, right? Now, go stand on your grass. Can't feel as much radiation coming off, can you? Okay. Dark color, light color, right? That's kind of the way this works. So usually I take people out to HCC and we go out in the parking lot. I know, it's dangerous. We go out in the parking lot and we stand on the blacktop. And you can feel the heat on your legs. And then we come back and we go on the grass. And you can't quite feel as much heat. I mean, you can still feel, I mean, it's hot outside, right? But you can't feel as much. Blacktop, you can feel the heat on your legs. Grass, not so much, right? That's just this. Objects that are good absorbers of radiation are also good emitters of radiation. That is the laws of radiation at work. And I'm trying to picture you going outside and putting your hand over the hood of your car, and then running over to the grass, standing there for a minute, and then going back, putting your hand over the car, and then going back to the grass. And it's kind of a funny sight. I can just imagine what your neighbors are thinking. That would probably mess with them. That sounds fun. You know what? I'm going to go outside and do that. I guess I will talk to you guys later.